In this lesson, we're going to cover the integral test, p-series, and the remainder estimate of sums. For the integral test, it says suppose f is a continuous, positive, decreasing function on the interval from 1 to infinity, and let a sub n equal f of n. Then the series, and we have sigma n equals 1 to infinity of a sub n, is convergent if and only if the improper integral, and here we have the integral from 1 to infinity of f of x dx, is convergent. So in other words, if we have the integral from 1 to infinity of f of x dx is convergent, then we can conclude that the series is convergent. If we have that the integral is divergent, then we can conclude that the series is divergent. Then we have a note: in order to use the integral test, n does not have to start at 1. So for example, if you're testing a series like this where it says n starts at 4 and goes to infinity, and you have 1 over n minus 3 quantity squared, we use the integral from 4 to infinity of the function. Next, it says it is not necessary for f to be decreasing over the entire interval. It is important that f be ultimately decreasing, that is, decreasing for x larger than some number n. This example says determine whether the series is convergent or divergent, and we're going to use the integral test. So here we have sigma, we have n equals 1 to infinity of e to the negative n. So over here I drew the function e to the negative x. Remember, e to the x goes like this, and when you have a negative in front of the x, it reflects across the y-axis, so it makes the graph go like that. And as x gets larger and larger, this graph is still continuous, it is positive, it stays above the x-axis, and it is decreasing. So it satisfies the three conditions in order to use the integral test. To set up our integral for the integral test, we do the integral from 1 to infinity, and again, it's 1 because this started at 1. And then instead of writing e to the negative n, we're writing e to the negative x. From one of our previous lessons, at this point, we can't evaluate our integral as is because the upper limit is infinity. So the first step we do is we rewrite it using limit as t goes to infinity. And then we replace this infinity with t. Okay, so now at this point, we're ready to integrate. So the integral of e to the negative x is going to be negative e to the negative x. And now we're going to plug in t minus plugging in 1. So we have the limit as t goes to infinity of negative e to the negative t plus e to the negative 1. I took this function and graphed it over here, negative e to the negative x. Remember, just e to the x goes like this. When you have a negative in front of the x, it reflects across the y-axis, so it goes like that. And then this negative in front reflects across the x-axis, so then it looks like this. So as t gets larger and larger, the graph approaches 0. So as t gets larger and larger, the limit of this term goes to 0. And this is a constant, so the limit of a constant is just that constant. So we end up getting 1 over e. So I wrote it out: since the integral from 1 to infinity of e to the negative x dx converges, by the integral test, our series is convergent. For part b, we have sigma n starts at 1 goes to infinity of 3n plus 2 over n times the quantity n plus 1. So when I plugged in 1, I got 5 halves. Plug in 2, you get 8/6. Plug in 3, you get 11 over 12, and then 17 over 30. So you can see by these terms, they are positive, and if you look, the terms are getting smaller, so this is decreasing. And then finally, about being continuous, if you look at this, it has vertical asymptotes at 0 and negative 1, but we're looking at the interval from 1 to infinity. So the vertical asymptotes at 0 and negative 1, where the function's not defined, is not in our interval, so we're good. This function is continuous. Okay, so we're going to apply the integral test. So we set it up. It's the integral from 1 to infinity of 3x plus 2 over x times x plus 1 dx. So our first step is we're going to write limit as t goes to infinity in front, and then we'll replace this infinity with t. At the same time, looking at this function, we're going to integrate it. And because the denominator factors, and then also the degree on top is 1, the degree in the denominator is 2, it's a proper fraction. So what we do is we're going to need to do partial fraction decomposition. So our first step for partial fraction decomp is I took the x and the x plus 1 and split it into two fractions. We have x and then x plus 1. They're both linear, so that means both of the numerators are going to be constants. So I just did a and then b. Next, we're going to multiply this whole equation by the quantity x times x plus 1. So when we multiply this side by x times x plus 1, it'll cancel off the denominator, so you just have 3x plus 2. Over here, when we multiply both of these terms by x times x plus 1, you're left with a times x plus 1. So you get ax plus a, and then we're multiplying b by x. So now to set up our system of equations, we're going to look at our x terms first. So we have ax plus bx, and then over here we have 3x. So that means we're going to set a plus b equal to 3. And then for our constant, we have a equals 2. So now if a is equal to 2, we can plug that in right here, and we're going to get that b is equal to 1. So since a is 2 and b is 1, we'll plug them in here and here, and then rewrite this as 2 over x plus 1 over x plus 1. And we're ready to integrate. So when we integrate 2 over x, we get 2, the natural log of the absolute value of x. And for this fraction, to integrate it, technically we're supposed to let u equal the denominator, but when you take the derivative of that, you just get 1. So then taking the derivative doesn't generate a constant, so you have 1 over u. The integral of 1 over u is ln absolute value of u, and then we'll plug the u back in, which is x plus 1. So again, when we integrate these, you get this expression right here. So now we're going to take t and plug it in for x, and then we're going to subtract, plugging 1 in for x. So here I plugged in t for x, and then over here I plugged in 1 for x. So I just dropped these terms down. Over here, the absolute value of 1 is 1. The natural log of 1 is 0. So that term's just 0. And then over here we get 2. The absolute value of 2 is 2. So we just have minus natural log of 2. And finally, we're looking at the limit as t goes to infinity. So as t gets larger and larger, both of these terms are going to grow without bound. So this entire thing is going to go to infinity. And I wrote it out. Since the integral from 1 to infinity of our function diverges, by the integral test, the series is divergent. For part C, we have sigma n starts at 1, goes to infinity of n over n to the 4th plus 1. So the first thing I did is I rewrote this as a function over here. So we have x over x to the 4th plus 1. And looking at this function, you can see that it will be continuous on the interval from 1 to infinity. As you plug in values for x, your terms are going to be positive. And then as you plug in larger and larger values, the terms are going to get smaller, so this function is decreasing. So since all three of these are satisfied, we can apply the integral test. So our first step is we write the integral from 1 to infinity of x over x to the 4th plus 1 dx. Next, we're going to put limit in front as t goes to infinity and then replace this infinity with t. At the same time, looking at this function, I'm going to rewrite this as x squared squared. So now what we can do in order to integrate this is we're going to let u equal this inside function x squared. So I wrote that here, we're going to let u equal x squared. So now we're going to take the derivative. So you get du dx equals 2x. So we rewrite this and we get dx equals du over 2x. Okay, and then also we have upper and lower limits, so we'll convert those. So we're going to plug in t right here for x, and then we're going to plug in the lower limit 1 in for x. Okay, so now we have everything ready to plug back in over here. So I took the converted upper and lower limits and plugged them in, so we have t squared and 1. I'm dropping down this x. Instead of x squared, we're going to put u, so that makes u squared and then plus 1. And finally, in place of dx, we're going to put du over 2x. So it works out great because this is the rigged part of the problem, so that cancels with the derivative, this x right here. And then I'm going to pull this 2 to the front as a 1/2. And now we're ready to integrate because the integral of 1 over u squared plus 1 is going to be tan inverse of u. And then remember, because we converted our upper and lower limits, we don't plug u back in. Instead, we just take these converted limits and plug them right in. So we're going to plug in t squared minus plugging in 1. So we have that written out. We have tan inverse of t squared minus tan inverse of 1. All right, so evaluating this limit, a couple of things are happening. First, we have tan inverse of t squared, which you can kind of just think of tan inverse graph. As t gets larger and larger, or as x gets larger and larger, the graph is going to approach the height of pi over 2, which is this upper horizontal asymptote. And then we also have tan inverse of 1. So tan inverse of 1 is equal to an angle. So then next we rewrite this as tan of what angle equals 1. Because the original problem had tan inverse in it, we're only looking for answers between negative pi over 2 and positive pi over 2. And then the acronym All Students Take Calculus tells us which trig function is positive in which quadrant. So again, we're only concerned with these two quadrants. All the trig functions are positive up here, and only cosine and secant are positive down here. So since this says tangent of theta equals positive 1, that means we want to look for our answer up here in quadrant 1. And we get that theta is equal to pi over 4. So again, tangent of pi over 4 equals positive 1. So instead of tan inverse of 1, I'm going to plug in pi over 4. All right, we're almost there. So again, evaluating this limit as t gets larger and larger, we already determined that this is going to approach a height of pi over 2. And the limit of this constant is just that constant. And then finally, we're just going to combine these fractions. So 1/2 pi minus 1/4 pi is 1/4 pi. So our final answer is pi over 8. And I wrote it out. Since the integral from 1 to infinity of our function converges, by the integral test, our series is convergent. Our next definition is a p-series. We have sigma n starts at 1 goes to infinity of 1 over n to the p, where p is a constant. So n's your variable and you're raising it to a constant power. So anything in this form is called a p-series. If p is greater than 1, the p-series is convergent. If p is less than or equal to 1, the p-series is divergent. This example says determine whether the series is convergent or divergent. For part A, we have sigma n starts at 1 goes to infinity of 1 over n squared. So this is of p-series form, and p is the exponent on the n, so p is equal to 2. And then let's go back and check. 2 is greater than 1, therefore the p-series is convergent. And then I just wrote it out that the series is convergent. For part B, we have sigma n starts at 1 goes to infinity of 1 over the square root of n. So our first step is to rewrite this so it's in the form of 1 over n to the p. And to do so, we rewrite this as 1 over n to the 1/2. So we have that p is equal to 1/2. And then I'm going to look back up here again. 1/2 is less than or equal to 1, therefore the p-series is divergent. So again, I just wrote it out, therefore the series is divergent. So for part C, we have the series written out in expanded form. It says 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus 1 over 4 root 4, and so on. So what I want to do is rewrite this in sigma form. And you can see that 1 was plugged in to get the first term, 2 was plugged in to get the second, and then 3, and so on. So we can write this as 1 over n times root n, where if n starts at 1, you start by plugging in 1 and you get 1. When you plug in 2, you get this term. When you plug in 3 for n, you get this term, so it works. Next, we're going to rewrite this expression. So n times root n is the same as n to the 1 times n to the 1/2. So that's going to be 1 over n to the 3/2. So now this is of p-series form. So p equals 3/2, which is greater than 1. Therefore, the series is convergent. So I just wrote it out, therefore the series is convergent. Our next definition, it's the remainder estimate for the integral test. It says suppose f of k equals a sub k, where f is a continuous positive decreasing function for x greater or equal to n, and the series is convergent. If r sub n equals the total sum minus the partial sum, then we have this inequality. It's the integral from n plus 1 to infinity of f of x dx is less than or equal to r sub n, which is less than or equal to the integral from n to infinity of f of x dx, where r sub n is the remainder. So s right here represents the actual sum of a series. S sub n is the partial sum, so it's kind of like taking your series out only like to 10 terms. Obviously, finding the actual sum versus a partial sum, there's going to be some variation in those two answers, and that's represented by r, the remainder. So when we apply this inequality, I have a note that you can use either side of it. So I just highlighted over here, this is the one I usually like to use. Finding that remainder is going to be less than or equal to calculating the integral from n to infinity of f of x dx. This example says consider the series. We have sigma n starts at 1 to infinity of 1 over n to the 4th. Part A says approximate the sum of the series by using the sum of the first 10 terms, or we call that the partial sum, s sub 10 of the series. So we're looking at the series where we start at 1, we stop at 10, and we can also denote this partial sum as s sub 10. So we're going to first plug in 1 for n, and we just get 1. Then we're going to plug in 2 for n, so we get 1 over 2 to the 4th. Then we continue by plugging in 3 for n, so we get 1 over 3 to the 4th. Plug in 4 for n, so 1 over 4 to the 4th, and so on. So we stop by plugging in this upper index 10, so we plug in 10, and we get 1 over 10 to the 4th. So again, you see that we plugged in 1, 2, 3, 4, all the way to 10, and then we stop. And that's how we're calculating the 10th partial sum. When plugging it into the calculator, you can totally just plug in 1 plus 1 over 2 to the 4th, plus 1 over 3 to the 4th, and so on. And if you have a graphing calculator, you can put this straight in the calculator by pressing the math button and then 0, and it will pull up sigma, and then you just fill in 1, 10, and then the formula. So S sub 10 ends up being 1.082. Part B says to estimate the error. So when it says error, we're talking about this value r. And again, r represents s minus s sub n. So s is the total sum minus the partial sum. So this would be the total sum represented by s. So if we found this value, versus finding S sub 10, which is 1.082, there's going to be a difference between this total sum and the partial sum, and that's represented by R. But since we're not going to find the total sum, we're instead going to find a value for R by using this inequality right here. R is less than or equal to the integral from n to infinity of f of x dx. So this is what we're going to set up for part B. So since we found S sub 10, the 10th partial sum, we're finding the error that goes with that. So that's going to be written as R sub 10. And according to the inequality formula, it's going to be less than or equal to the integral from n, or 10, to infinity of the function 1 over x to the 4th dx. So what we're going to do is we're going to calculate this side of the problem. In order to evaluate the integral from 10 to infinity, our first step is we're going to write limit as t goes to infinity, and then we plug in t for infinity. And I also rewrote this as x to the negative 4. Okay, at this point we're ready to integrate. So the integral of x to the negative 4 is 1 over negative 3x to the negative 3. Now we're going to plug in t minus plugging in 10. So we get 1 over negative 3t cubed, and then plus 1 over 3 times 10 to the third. And then taking the limit as t gets larger and larger, this term is going to go to 0, and then the limit of this constant is just equal to that constant. So you get 1 over 3,000. So R sub 10 is less than or equal to 1 over 3,000, or 0.0003 with a bar over it. So calculating the 10th partial sum as opposed to calculating the actual sum, if you do that, the error is going to be at most 0.0003 repeating. All right, guys, thanks so much for watching.